Hi everyone. In the last video that we did, I left you with a question, and the question was, can you work out what the gradient of the line y equals 2x minus 1, y equals 2x minus 1, using limit theory. Now, I should start by saying, of course, that we already know what the gradient of y equals 2x minus 1 is. It's 2. It's the value before x when the line has been written in gradient intercept form, like this line has been. So we've got y equals 2x minus 1. So if I drew that graph, really rough sketch, we would have the y-intercept at -1, and it goes up with a gradient of 2. So we know that the slope's going to be relatively steep, but instead let's just solve for x. So to get the x-intercept, so we got 0 equals 2x minus 1, 2x is equal to 1, x is equal to a half. So that's where the x-intercept is. And then I'm just going to get my ruler here, and I'm going to do a dot-to-dot join the two lines together. And there we go. There's a sketch of my graph. I'll just be a good boy and label my axes. Okay, so that's what it is. I mean, we can see now. We should see that the gradient of a straight line, of course, is like the equivalent of the average, I suppose. The gradient doesn't change. That's what makes a straight line graph. All along the line, the gradient is exactly the same all the way through. It's a constant gradient. So it's no surprise that the gradient function is a constant number. That number 2 there is constant. It doesn't change. It doesn't matter what value I give x, the gradient will still be 2. The gradient is 2 there, the gradient is 2 there, the gradient is 2 there, all the way along the line the gradient is 2. So that's no surprise. The average gradient, which would be taking any 2 points and working out the gradient, is 2. So the average gradient, the instantaneous gradient, the gradient all along the straight line is 2. I think I've said that enough, right? The gradient is 2. Okay, so we'll move on from that. So if limit theory is worth anything, then if I apply the same concept of limit theory to this formula, to this function, then I should get 2, right? I mean, that's hopefully obvious. So let's start again, and I'll write the function with f of x this time. It's just the same as y, really. I'm just using different notation. So f of x is equal to 2x minus 1. Now, the limit theory says that the gradient is the limit as h approaches 0 of f of x plus h. That means instead of x, I put x plus h in my formula, or my function, and then I take away f of x. So remember, that's the rise part, and then the run, remember, is just h. X plus h minus h, x plus h minus x, which equals h. Okay, so I have f of x plus h minus f of x. Okay, so we'll work that out. Limit as h approaches 0. Now, f of x plus h, so if the formula is, sorry, I keep on calling it formula, but it's function. If the function is 2x minus 1, then at x plus h, the function is going to be is going to be 2. And instead of writing x, write x plus h. So I'm just replacing the variable x with the specific point I'm looking at, which is x plus a little bit, x plus h. Okay, so it's 2 outside of x plus h minus 1. Okay, so that's f of x plus h. Minus, and I think I'll put my brackets in here because I'm dealing with negatives, and whenever I'm dealing with negatives, I make sure that I keep my brackets going just for a little bit. So minus 2x minus 1 all over, where'd that line go? All over h. So just to color code that, I've got this bit here is f of x plus h. Okay, and I'll use purple. And this bit here is f of x. Okay, so I've subtracted f of x away from f of x plus h. I've subtracted 2x minus 1 from 2 times x plus h minus 1. Okay, replaced x with x plus h. It's really critical. I'm sorry to go over and over and over the same point, but it's really important that we understand that. Okay, let's keep going because that gets us to our answer. No duh. Okay, so the limit as h approaches 0. So I'm going to expand that. So what do we got? 2x plus 2h minus 1, and then I'm going to expand, I'm going to put the negative inside the bracket if you like, so it's minus 2x plus 1, the minus minus 1 becomes a plus 1, all over, oh that line's gone again, all over h, there we go. Alright, simplify the top and that gets us closer to the solution. The limit as h approaches 0 of, well let's see, I've got a 2x here, and then I take it away over here, so that's 0. I've got a minus 1 here, which I then add 1 to, that makes it equal to 0 too. So that leaves me with 2h over h. Cool. Let's cancel down. There's an h on top and an h on the bottom. And that leaves me with the limit as h approaches 0 of 2. That's all I've got left. And now I set h equal to 0 to say, well, now I'm going to make h approach 0 and get to 0. What happens to the gradient function? And of course, since there are no h's, it's just 2. There we go. So the gradient is equal to 2. Now, of course, in a linear function where we've got the linear function, where we've got it in gradient intercept form already, or any other form really, it would be easier just to put it into gradient intercept form and then say, well, there we go, there's my gradient, it's 2. So I understand, but I guess this is proof of concept really, that limit theory does work for any function, and here's another example of it working. In this case, it works for a linear function. There we go, so the gradient is 2. Now, before I wrap up, I want to do a little bit of language around this idea of a gradient function. So far, I've been using m for the gradient, okay? But m is really reserved for linear functions. It has a special meaning, I suppose, which is why we really only use it in linear functions. So y equals mx plus c. And this idea of a gradient for quadratics or for cubics or for other functions, we need a bit more of a catch-all phrase. Now, generally speaking, if you remember when we looked at the quadratic, the linear function was a the gradient function was a function as well. So rather than give it a single letter like m, which tends to imply it's a single number, we use different function notation. So rather than m, there's two notations that are used. There's this one here, and this will be the one that I tend to use most of the time. We say f dash of x. That's how you say it. So the dash means that the function has been derived into a gradient function, and we call this the derivative. It's the derivative of the function. You can use it with linear functions. You can say f dash of x is equal to 2. You can use it. It's a catch-all phrase. So m, special just for linear functions, f dash of x. We use that for any function to say this is the gradient. F dash of x is the gradient function of f of x, or the derivative of the function. There is one other. It's a little bit more old school, but you will come across it. It goes like this: dy by dx. Often used when you're using y equals something rather than f of x equals something, and dy by dx simply means, think of it like this, think of it like d means, it's short for the Greek letter delta, and delta is often used in mathematics to describe a movement or a change. So little dy by little dx is like saying a small change in y, so a small change in y for a small change in x. And that's basically what f of x plus h minus f of x is. That's the change in y, and x plus h minus x is the small change in x. So we can use dy by dx, and that's how you say it, dy by dx. Yeah, so again, it's kind of like small change in y by small change in x. Okay, so it means the same thing. It's the derivative of a function, and you say dy by dx. All of these things effectively have something to do with gradient. With f dash of x and dy by dx, we're often left with a function as opposed to a number. So I'll put that in brackets because you don't normally call m a function, but it kind of is. It's a constant function, right? It's constantly 2 in the case of the previous example. So it's a gradient function, and the gradient function, if you remember, allows us to work out the instantaneous velocity of a function. So f dash of x is the gradient function, which allows us to find the gradient at any point of our function. Okay, I think that's where I'll leave the video now, and yeah, next video we will have a look at using f dash of x a bit more in order to have a look at some results with sort of some power functions. More on that next video.